essentially finishing off today implicit differentiation. I'm going to try my best to get as far through the last section, which is logarithmic differentiation. So let's begin. We already have done lots of questions on finding first derivatives. I'm going to do one more where we get to find the equation of tangent lines. And then the last thing we're going to do is find first and second derivatives of implicit expressions. And these questions are horrible, relatively speaking. But the first one I'm going to do is an example of that one. And there's a cool little curve. This is number 11, which is y squared take away 9 equals x squared take away 11. So that's the implicit expression. And we are being asked to find the equation of the tangent line at that point. And this is not me making this up because I'm reading it in front of me. That's called the devil's curve. No idea why. I'm just reading what I say. So this fella is called the devil's curve, and we're going to find the equation of the tangent line at that point. Now, when you look at an expression that's quite messy like that, your first goal should be, or your first motivation should be, I want to make this as easy as possible on me. I want to do the least amount of work to get the answer. Now, I could leave both of these as is, but wouldn't that be a product rule and a product rule? And would you agree that's probably going to be really ugly on the left-hand side? And so I'm thinking to myself, I want to avoid that. So what I'm going to do, because these are not that bad, is I'm going to distribute them. I hope you agree that that's easier and less work to differentiate than that guy is, right? So, you know, whatever you've got, work with it, right? Do the best you can. Now, differentiating this guy gets you 4y cubed to y by dx. Differentiating this guy gets you negative 18y dy by dx. Differentiating this guy gets 4x cubed, and differentiating this guy gets you 22x. I mean, that went really smoothly. Would you agree? There wasn't really any weird stuff going on. It was pretty straightforward. What should I do next? That's pretty standard. What should I do on the left?
Factor out dy dx.
Have you noticed that that line where you factor out the dy by dx is kind of guaranteed to happen in these questions, just the way the math works? You're going to probably have to do that. And in the same vein, don't you always kind of finish with a divide? Don't you divide both sides by something? And so we're getting kind of comfortable, I hope, that when you do implicit differentiation, that's the kind of thing that could happen. Okay, sometimes you get style points, sometimes you don't. But in this case, I would say there are some style points. So any factoring you can see, top or bottom, tell me and I will do it.
The 4.
Can you get 4 out of both, or could you do, maybe you have to go a little bit lower? I don't think I can pull out a common factor of 4 from here or here, but I could do something that is
2x on the top and 2y on the bottom.
Okay, so just a little bit less, right? 2's will do. Now, if you take 2 and an x out of that, you're still left with 2x squared. Take away 11, and here you're going to get 2y squared. Take away 9. Right, we're after the equation of a tangent line at that point. So the x coordinate is going to be 0. So the slope of the tangent line is going to be, well, I should say x and y coordinate in this case, is going to be at the point 0, negative 3. So that's 2 lots of 0. 0 take away 11 over 2 lots of negative 3. 2 lots of negative 3 squared, take away 9. And after doing all that, I just noticed, couldn't I just have said the answer was 0? Because the minute you stick a 0 here, you know, isn't the whole answer going to be 0? Because any number times 0 gets you 0. So who cares what the other numbers are, right? And who cares what the bottom is, right? Boom, 0. Okay. So we have a slope of 0 passing through that point. I really don't need to use the point slope equation, but I'm going to use it anyway, just to show you can use it in every situation. It's y take away -3 equals 0, x take away 0. So you have y plus 3 is 0, and so you have y equals -3. So in fact, that is a horizontal tangent line. Horizontal tangent line, y equals -3. So I have already set this guy up, and I've put it into Desmos, so I know I'm correct. And here it is. This red curve, why it's called the devil's curve, I have no idea. But evidently, that's its name. The point that we're interested in is down here, right? And can you see the tangent line, which is y equals -3, is exactly what it said it would be. It's a horizontal line, y equals -3. When you see things like that, it's kind of comforting, isn't it? Oh, I must have done it right. And that is kind of the end of that. I'm going to do something here. I'm getting a kind of weird feedback. I don't know if you are. There we are. So you have to hit the space bar now if you want the answer. I hope you do. And we're now going to be on the last piece of the puzzle. How do you find first and second derivatives of implicit expressions? And I promised you that they were going to be ugly. Not that I wanted them to be ugly, but that's just what they're going to be. Well, let's pick one. The one I'm going to do is question 14, or at least like it, but 13 and 15 are very similar. So what you're going to do is use this as a template to how to do these questions. Typically, finding the first derivative is not going to be a problem. The ugliness happens when you have to find the second derivative. So here goes. Differentiate everybody. 2x. This guy is f and g, so I'm going to do a product rule on that one. And this guy here is going to be 2y dy by dx, and the differentiation of 9 gets you 0. So this guy in the middle is f dash g plus f of g dashed. Right, if you have two things multiplied together, two x's, right, or an x and a y in this case, it's going to be a product rule. So I have a 2x, f dash gets me 1, leave that guy alone, plus leave that guy alone and differentiate y. Technically, if you differentiate y, you get 1 times dy by dx, and everything else hasn't changed. So what I'm going to do, well, I'm going to put this line in for my benefit, just makes it look cleaner. Now, in the big scheme of things, that should not be that bad a question, right? We've done enough of these to be comfortable, I hope. Now, the finish of the process is going to be pretty much standard. Aren't I going to keep these two guys on the left because they both have a dy by dx attached to them? And these two guys here, aren't they going to end up over here? So I'm going to subtract 2x from both sides. I'm going to subtract a y from both sides. So when I do that, I'm going to have an x dy by dx plus a 2y dy by dx. Take away 2x from both sides, take away a y. And just like I did at the start of today, aren't we going to finish with the same kind of two lines that we typically finish with? Pull out a common factor of dy by dx and then finish with a divide. So this process of finding the first derivative using implicit differentiation kind of has a flow to it. You know, the last two pieces of the process are almost always going to be pull out a common factor, right? And then do this. So far, so good. First derivative, done. What's different? They also want the second derivative. And this is where the problem starts. And it's a biggie. I'm just rewriting this guy here because I want to start on the top of a page. Right. Don't need that guy anymore. Get him out of the way. If I want the second derivative, I know it's clunky notation, but that's the notation for the second derivative. Doesn't that mean then I have to differentiate an ugly fraction? And remember yesterday I said, look, fractions are horrible. If you can find a way of not having a fraction, like cross multiply, whatever it is, do it. You can't avoid it when you do second derivatives. You're going to have a fraction, you're going to have to deal with it, which means I'm going to have to use the quotient rule. So it's going to be f dash g, take away f of g dashed, all over g squared. I'm going to put this guy along way over here. If you differentiate the top, put little brackets around it, right? If you differentiate the top, you get -2, and if you differentiate that guy, you get -1 times dy by dx. So that's that guy done. Times the untouched g. Take away the untouched f, and then you differentiate the bottom, and you get 1 plus 2 dy by dx's all over the bottom squared. Would you agree that that is horrible? That is ugly. And the second derivative doesn't follow the same flow as the first derivative. Have you noticed that there are two, in this case, there are two places where there's a dy by dx? Right? Two different places. And we're going to have to deal with that, right? But let's hold off and worrying about dealing with that. And let's just focus on what the heck's going on here. Right, I have to make it look pretty. So I'm going to foil these two things, and I'm going to foil these two things. Don't worry about dy by dx. Treat it like, you know, I don't know, x squared or 42. It's just a term, right? Foiling it the same as everyone else. So -2 times that gets me -2x. -2 times that guy gets me -4. That guy times that guy gives me -x dy by dx. And that times that guy gets me -2y dy by dx. Are we okay with that? Foil it out. While I'm at it, I may as well do the whole stuff on the bottom squared. Right, now I'm going to multiply this guy by this guy, and then I'm going to also have to factor in this negative. So watch me in case I screw up. -2x times 1 is -2x, then you take its negative, so it ends up positive. -2x times that guy is -4xy dy by dx, but then it's positive. So you get 4x dy by dx. If you do that one by that one, you get a plus y. If you do that guy by that guy, you get a plus 2y dy by dx. Are we good so far? There is nothing pretty about this expression. And you've got 3 of them to do, so have fun when you get to do the others. Now, at this point in time, would you agree it would be a good idea to collect like terms, see if anybody cancels? So can you see anything that cancels out with anybody else from this big list of, what, 8 different terms? Can you see anything that cancels out with anything else?
Negative 2x, positive 2x,
Okay, agreed.
negative 2y dy dx, and positive 2y dy dx.
Agreed. Anything else? I think that's it. Would you agree? In case I missed one, tell me.
Could you subtract the negative x dy dx from the 4x dy dx? And
Okay.
also the 4y from the regular y.
Okay, agreed. And so we combine these and get 3x, and we combine these and get negative 3y. So we have a negative 3y and a plus 3x dy by dx. I mean, very, very slowly, isn't this answer getting a little bit nicer? Just a little bit nicer. It's still pretty yucky looking, but it's better. We have one issue, and we're finished. What the heck are we going to do with this dy by dx? Because it isn't allowed to stay there. The answer must contain only x's and y's to be finished.
Multiplied by dx over dy.
What an interesting thought. No, but I like the thought. I'll give you a clue. Don't we already know what dy by dx is? Because we found it over here. So, as bad as it is, doesn't that guy equal this guy here? Yep. Just when you thought you'd killed all the monsters, this monster appears. We have the second derivative, and it is not looking good. Would you agree that this is a fraction, this isn't a fraction, and we don't like fractions in fractions? So this is correct, and if you're really lucky, style points will be your friend and allow you to write that down as an answer. And if you are not, of course, we have to figure out how to make it look pretty. I'm essentially writing the same thing down again, but just separating out this a little bit more. And I am now going to multiply the top and bottom. So this is how you get rid of the fraction, by a special version of 1. So the bottom will now become x plus 2y cubed. This guy times this guy gets you negative 3 lots of x plus 2y. And this fraction times this one gets you plus 3y, negative 2x, negative 1. So I have managed to get rid of the fraction. And I'm quite happy with the way it looks, but I think I can make it look a little bit nicer. Negative 3x, negative 6y, negative 6xy. Oops, it's going to be a negative 3y squared. There we go. No fractions, everything with x's and y's. Can't really do much in the way of common factor. I guess I could pull out a 3 counter, but I'm not too bothered about that. Nothing else works. So you can imagine the last 3 questions are going to be horrendous. Second derivatives are never, ever nice. Right? They are just messy mess. But it's done. So that's good news. Are we good with implicit differentiation? As far as you can handle it. Okay. Our next guy in town is this one. Logarithmic differentiation. Now, implicit differentiation is a little niche market, right? It allows you to differentiate implicit expressions, right? Things with x's and y's all jumbled up. Implicit differentiation is the way to go. The most likely question will be find the first derivative. Sometimes when they're being really nasty to you, they'll ask you to find the second derivative. So what is logarithmic differentiation? Well, it's a process that allows us to differentiate very, very strange, and call them exotic derivatives. Derivatives that you wouldn't even probably think about. We are going to, if we get to it today, find how to differentiate that. Would you agree that is a pretty weird looking function? Typically, logarithmic differentiation is used to find a derivative of very unusual powers. And no, the answer to that is not x times x to the power of x minus 1, right? I wish it was. I truly do. It would make life so much easier, wouldn't it, if you just said, I'll do a power rule on it. It is much weirder than that. And that's what logarithmic differentiation is going to do. And again, it's not a formula. It's not like the product or quotient rule. It's more like a process, right? So the chain rule is a process, really, although it has a pretend formula that you never use, right? So the chain rule is a process. Implicit differentiation is a process. Here is our last guy. Because once we know how to do logarithmic differentiation, that's pretty much all the techniques that we need to worry about. So everything that you're going to differentiate will be one of those product, quotient, chain, implicit, or logarithmic differentiation. So that's kind of nice once we finish this. So I'm going to start with what is called the laws of logs. Because we are going to be dealing with logs, and so we need to know how to, the algebra of them, how to manipulate them. So there is the log of A plus the log of B. If you add two logs together, it's the same thing as the log of AB. Do you remember saying that law? And log could be log to base 10, log to base E, which is called the natural log. Doesn't matter. So I'm saying this is true for all bases. Now, if you do the log of A and you subtract the log of B, you'll get the log of A divided by B. You remember that guy? It's called the second law of logs. And the third one says some number n times the log of A will get you log A to the n. And you use the rules going in both directions. So if you tell me this, I can combine them. If you tell me this, I can break them apart, right? It works in both directions. Now, the most common log that you're going to be dealing with in mathematics is log to the base E. Right? Remember E 2.71, the same E as E to the X. It's called the natural log. And it's very often, including in your calculator, it's written as ln of x. Right, so if you ever seen your calculator ln of x, it's that guy. The only other button that your log button that you've got in your calculator, I believe, looks like that, doesn't it? Do you know what base that is, even though it doesn't write down what base is? That's actually log to the base what? 10. Okay, yeah. Now, you're not going to deal much with that guy. Focus on this guy, because in calculus, e to the x is much nicer than 2 to the x. Agreed, right? Most things are in e to the x format. In calculus, most things will be the natural log rather than maybe log to base 10. Log to base 10 has a niche market. It's used in the Richter scale for earthquakes. It's used in the pH scale in chemistry, right? So there are places where the log to the base 10 is used, but in general, natural log is your guy. So, a few other things. What is the natural log of 1? What number is the natural log of 1?
That'd be
Be what?
0.
0. In fact, any log, if you evaluate it at 1, is 0. But the natural log is obviously that. Another one that we'll probably be dealing, we will be dealing with is, what number is the natural log of e? Right, 2.712. What's that guy?
1.
It's 1. So we are going to be using some of these properties to help us find derivatives of log functions. So the first thing we're going to do is we're just going to look at differentiating functions with logs in them, right? So we're not doing logarithmic differentiation yet. We're only doing functions with logs in them. And there are 13 of them. So let's get started. Suppose I give you a function like that, and I ask you to differentiate it. Do you, oh, rewind. I forgot the most obvious thing. Jumping ahead. I haven't told you what the derivative of the log function is. I forgot that one. Some of you may have picked it up from high school or just picked it up from somewhere. So I'll ask in case we have it. Does anybody know what the derivative of the natural log function is?
1 over x.
1 over x. Technically speaking, it's 1 over the absolute value of x, but let's just call it 1 over x. The reason they stick an absolute value on it is to be a lawyer. If you do the log function, it only exists for values of x bigger than 0, right? So nobody would ask you to find the log of 1 over x, or find the derivative, I should say, of the log of x at x equals minus 20. Would you agree? Because the function doesn't exist there, right? It would be a silly question to ask. And that there covers that. So 1 over x is fine. Of course, there are other logs. And we need to know a couple of questions anyway. We need to know what the derivative of this guy is. And he is actually going to have a 1 over x base to it. But he also has a weird constant that goes here. And that weird constant is the natural log of whatever that base is. So if you want to find the derivative of log to the base a of x, it's 1 over the natural log of a x. Okay. So you just remember those guys, right? Derivative of natural log is 1 over x. The derivative of a log to base a is 1 over the log of ax. Now we can go to this question. This fella is a chain rule, and the inside function is 3x plus 1. So if I want to differentiate that, you get 1 over 3x plus 1 times the derivative of the inside function, which is 3. And your answer ends up being that guy. That wasn't too bad. Suppose I give you an x squared, the natural log of x. Would you agree this time it's a product rule? So I want to differentiate a product. It's f dash g plus f of g dashed. So differentiate that guy, you get 2x. Leave that guy alone, you get natural log of x. Leave that guy alone, you get x squared. Differentiate a natural log, you get 1 over x. Should always tidy things up. That guy times that guy gets you x. x, and then some style points to finish. You're done. We're good with that one? Let's do something weird then. How about the cosine of 2 times the natural log of x? Would you agree this is a chain rule again? What would that be? What process would I use to differentiate this guy? That's the chain rule. What's this guy?
Product rule?
What's he now? Oops. What's he now? Chain rule. Do you see how simple, how similar a product rule and a chain rule could look? Right. If I stuck an x next to that cosine, wouldn't this now be a product rule? Without the x, it's a chain rule. With an x, it changes. So easy to, well, with my eyesight anyway, it's easy to miss something like that. So we are looking at the cosine of the inside function. So its derivative is negative the sine of the inside function times the derivative of that guy, who is 2 over x. And there's really not much you can do to this as far as style points go. That would be my answer. Now, this question doesn't look particularly different. Actually, this is number 4. Particularly different, but it is going to be different. And this one is going to be under my general, just because I can doesn't mean I should. I could differentiate that. I could say, okay, that is my inside function. I will use a chain rule. If I did do a chain rule directly, wouldn't I end up having to differentiate this as well? And if I wanted to differentiate this, wouldn't I have yet another chain rule? So it'd be a chain rule inside the chain rule. Isn't it quite hard to keep all those balls juggled and you kind of lose place very easy? So I'm not going to do that, although it could be done that way. I am going to use the laws of logs. So I'm going to call this the log of 4 plus the natural log of x squared. Because isn't there a rule that says 2 things multiplied can become 2 logs added? Are you comfortable? 2 things multiplied, 2 logs added. And then I'm going to do even more. Isn't the log of sine squared, can't it be written as 2 times the log of a sine? Right? Sine squared can become 2 times logs. So by using combination of these, I have taken the original one, which is pretty ugly and probably quite hard to do as a chain rule, and reduced it to this guy, which is a much simpler question. Would you agree this is easy to differentiate? So now I'll differentiate. Okay, what do you get if you differentiate the log of 4?
Four
It's a
over
number.
x.
It's
One
a
over-
number.
One
So
over-
not 1 over anything. Natural log of 4 is just a number like 1.8.
0.
You get 0. Isn't it one of those, the square root of 2 is just 0? 5 cubed is still 0. Right? Some numbers look weirder than others, but if it's a number, its derivative is 0. And that is a number. Couldn't you plug that into your calculator and get a decimal for it? Right? It is a number. Now you want to differentiate this guy. There's your inside function. So it's going to be 2 times 1 over the inside function times the derivative of the inside function. And so I'm now looking at that answer. Style point rule. 1, make it look like the original. Well, it's got sines and cosines in it, so that's good. Factor the heck out of it. Now, I can't say any factoring. But when it's trig, and this is trig, the third rule kicks in. Is there any way of rewriting that guy?
It's going to be
Tangent.
Cosine, cotangent.
Well, it's going to be a tangent, it's a cotangent, or some other thing. Look again. What's a cosine over a sine? It's a
Cotangent.
single thing. Cosine over sine. What are they?
Cotangent.
It's cotangent. And there you're finished. Now, you know a list of things that can turn into other things, identities in trig? That's one of them. I'm only doing question 5 to just show you a quotient rule. So that's going to be F, and that's going to be G. Are you comfortable? It's pretty obvious it's a quotient rule, right? There's no algebra I can do to make it nice, right? It is what it is. So just to mix and match the notation, there's the derivative. F dash G, take away F of G dashed, all over G squared. If you differentiate the top, you get 15. Leave the bottom alone. Take away, leave the top alone. And if you differentiate a log, you get 1 over x. And the whole thing is over the natural log squared. So I get 15 natural logs of x. You multiply these together and the x's cancel out. And I get that. And just to be perfect, why don't I pull out a common factor of 15? Yeah. Wasn't a much more straightforward question, right? There wasn't too many bits of algebra to concern us with. Any questions so far? So right now we're differentiating functions that have a log in them somewhere. Here is another one of those just because you can doesn't mean you should ones. I want to differentiate that function, but I do not want to do it as a chain rule with a product rule with a chain rule. I would screw up somewhere. Instead, I want to rewrite that guy using these laws into a much easier to differentiate thing. It might look bigger, which it will, but it will be easier to differentiate. So that's the advantage. If you think about this, isn't this like an A times a B? Isn't that 2 things multiplied? Right, and x times that's like an A times B. So that means I can split it up as the natural log of x plus the natural log of e to the negative 9x. Are we comfortable with that? That's basically this one here. Now, focus on this guy. Isn't this basically like an e to the power of n? It's an e to the power of 9x, right? But it's a power. So shouldn't I be able to write this as negative 9x, the natural log of e? Would you agree? E to the power of n in log a. I can do one more thing. What number is the natural log of e again?
1.
So wouldn't that just be 9x times 1? So it's 9x. I hope you agree with me. Isn't this guy a much nicer looking version of that guy? Isn't this guy going to be much easier to differentiate than that guy? Right? Isn't that guy going to be some horrible chain rule, product rule monster? Isn't this just going to be and the derivative is 1 over x minus 9 and everybody's happy. Algebra is your friend. Yeah, you might not like algebra. You might not like putting things together and pulling things apart and doing log rules on them. But if you can be good at doing that and know when to do it, can't you make your life a lot easier when you want to differentiate something? So always have a look at something and say, can I do better? Right, so I'm going to do another question, but I'm only going to set it up. I'm not actually going to take it to the end. I could differentiate this as basically a chain rule with a log involved. I mean, it would work. It's maybe not that bad, but it is pretty bad. Can anybody see a different approach? Let's use some of these guys. What would the square root of t squared plus 9 be inside a log? How could I rewrite it? Okay, while you're thinking, I'll give you some help. If I write it that way, does it help? How am I going to rewrite this guy using these rules?
It'll be the same as a half a log of t squared plus 9.
You nailed it. Would you agree that finding this derivative is going to be a lot less work than finding the original? Because if you had to do this, wouldn't the inside function be this guy? And that in itself would be a chain rule inside another chain rule, right? Be pretty messy. So now that I've got it in a format that looks nicer, it's a half times the derivative of this guy. So that's still an inside function. So it's 1 over the inside function times the derivative of the inside function. And you notice these two kind of give you t. So what you're left with is this guy. I mean, isn't that quite elegant? It's not that ugly an answer. If you just tackled it from the start, it's a bit wet, you'd eventually get that answer, right? You'd have to factor things and cancel and do all sorts of cool stuff. But that's just cleaner and quicker. So let's put in a log that isn't the natural log, because we haven't done one like that yet. Let's do a version of 8. Y is going to be the log to the base 5 of tangent x. Now, I can't do any algebra on it. This is going to be what it's going to be, right? I'm not going to change it. But I do notice, right, that it's a chain rule, and that is my inside function, right? So its derivative is going to use this rule. It's going to be 1 over the inside function. But because that's a 5, you tag on the natural log of 5, right? If that was 10, you put a natural log of 10 here. If that was log to the base 2, you tag on a natural log to the base 2, right? That's just what it is, right? And then I finish with, don't I? The derivative of the inside function. What's the derivative of tan x? And we should be quicker now because I've asked this a couple of times. Derivative of tan x.
Secant x tan x.
Try again.
Secant squared.
Yeah, you were close. Secant x is what you just said, Robert, so you're pretty close. Secant squared. Now, I have, I'm doing this really slowly, I have this guy. And I have this guy. And now I'm going to say that this answer could be prettier. And there's a rule, there's lots of rules with trig, but one of the rules with trig is try and avoid fractions. So I'm not going to use that tan x in the bottom because it's the same thing as a cotangent x on the top. So you might think there's not a heck of a lot of difference. I agree, there's not a heck of a lot of difference. But if you can take a trig and make it so there's no trig on the bottom, you should do it. Not that you'll be able to do it every time, but you could. So if there's a cosine on the bottom, won't you call it a secant, right? If there's a sine on the bottom, you're going to call it a cosecant. If there's a secant on the bottom, you're going to call it a cosine, right? So try and remember all the reciprocals of each other, and that allows you to no longer have a trig on the bottom of our fraction. Let's see if I can find another non-log one. Oh, here, didn't take too long. Question 10. Nine to the power of z times the log to the base 9 of z. Now, I can't do anything to make it pretty, so this is going to be a product rule. So we're going to do f dash g plus f of g dashed. Now, if you differentiate 9 to the power of z, you do get 9 to the power of z, but don't you get something else because it's not e to the z? If you differentiate 9 to the power of z, you get 9 to the power of z, but what goes here? What funny number goes here?
Natural log 9.
Do you notice in this case, it's a multiply, and in other cases, it's a divide, right? So that's a derivative times the untouched g plus the untouched that guy, followed by the derivative, the log to the base 9 of z. And isn't that 1 over z? And it also has a natural log of 9 going on. And I have natural log in 9, the log to base 9 of z, plus 1 over the natural log of 9z, and the whole thing, I'm going to pull out a 9 to the power of z. So there wasn't really much I could do except pull out this guy as a common factor. I'm not even going to attempt to make that look pretty. I'm not sure I could. Okay. Now I'm going to hit you with what at first sight will look horrible. I want to differentiate that. If you don't think about it and you jump right in the deep end, aren't you going to call this the inside function and jump into trying to differentiate the most horrendous looking chain rule inside a product rule inside a quotient rule inside a chain rule? I don't know if that's correct, but it's some weird combination. I don't even know where it would go, but it'd probably fill up this page. Would you agree that's probably not a good strategy? Right. But we have seen this before. Can't we use these guys to make this guy much nicer? So we're going to do that. this guy times this guy divided by that guy. So that becomes the natural log of this one plus the natural log of that one, take away the natural log of that one. Are we comfortable about this guy plus this guy divided by that becomes this log plus this log, take away that log? I'm basically using these rules, right? Are you comfortable with the algebra I just did there? Now, that's nicer, isn't it? That's a lot nicer as far as differentiation goes, but we can do better. Won't this one become 100, the natural log of x plus 1? And won't this one become 5 times the natural log of 2x plus 1? And hopefully now that you've seen this for the second time, you'll know how to rewrite this guy. The natural log of the square root of x plus 1. How will I rewrite that one?
Half in the natural log, half of the natural log of x
Yeah.
plus 1.
Yeah, the minute you said, I know, Matthew, you knew what to do, right? It's half of the guy. Now, in this format here, I think it's even easier to do than it was in that. And that was easier to do than that. So if you look at this and you look at that, I think there's no comparison. Isn't this much easier to differentiate? It just is. So these rules here are there to help you for questions, especially like this one. So if you differentiate this one, you basically get 100 over the inside function. But the derivative of x plus 1 is 1, so that's the final answer. And if you do this, that's x plus 1. Can I call that 4? Right. Doesn't change much, but I just want it to look nicer. So it's going to be 1/2 over 1 over x plus 4 times 1. And this guy is going to be -5 over 2x plus 1. And I have deliberately made a mistake. What's wrong with that third one? What have I missed? The derivative of that is 5 over this guy. That's what I wrote down. But I've missed something.
The inside.
And what does the inside get me? Doesn't it just get me an extra 2? Right? Derivative of 2x plus 1 times 2. See how it's very easy to miss a little baby chain rule, as I call them, right? A little 2x plus 1 thing. So what do we get? I have that guy over that guy over that guy. And we're done. I'm not going to try and combine 3 fractions. There is no advantage at all to doing that. Okay. I'm not going to do this question in total. I'm just going to set it up. I want to differentiate that guy. Would you agree it's probably not a good idea to jump right in and start doing chain rules? That's normally a sign that you should do something else. You should use these guys. So there's my first piece of algebra. Can't you break a square root of a fraction into 2 separate square roots? Right? That's allowed. Right, anybody want to have a shot at what the next line's going to look like then?
The log of the top square root minus the log of the bottom square root.
You nailed it. And I'm not going to ask you this time because this is what about the 4th time we've done square roots. Won't the next line be a half of this guy, take away a half of that guy? Would you agree that is much easier to differentiate? And you're going to get a couple of fractions, but it's okay to have fractions. So up to this point, all we've done is show you how to differentiate functions that have logs in them. You feel comfortable about the process, right? How to differentiate a function that has a log in it. So now we're going to do, as you might expect, find the equation of a tangent line. They always throw that in almost every case. There's only one of these, so let's do it. So the question is, find the equation of the tangent line to this curve at the point 1, 0. So I'm going to find its derivative. In this question, would you agree I don't have any of this stuff to do? I mean, it's just a product rule, right? It's not that ugly. It's a product rule. So it's going to be f dash g plus f of g dashed. And so I'm going to get the derivative of that, which is ex to the 7, times the untouched version of that, plus x to the 8, and the derivative of natural log of x is just this guy. And I'm looking at that. Is there any style points you can do to that question?
Remove x of 7, x to the power 7.
Okay. I want to check something here. That is very interesting and bad news as well. I want to check this if you hold on a second. I'm checking its answer because I think something very strange is happening. This is question 14. Okay. Okay. X is 1. So the derivative at 1 is 1 squared 8 times the natural log of 1 plus 1. I was getting confused here because of this guy, and I shouldn't be. What is that guy equal to? Big fat 0. And my brain was saying, why are we going to have a weird slopey tangent line? And there isn't, because isn't the answer just 1 times 1, which is 1. So the slope is just a nice number. I thought it was going to be, 8 log something plus 1 or whatever. And I'm thinking, what the heck is going on there? But it isn't. Right, so if we call this guy x1 and y1, and can I leave it there? Wouldn't you just do the y minus y1 thing and off you go? Nothing real, nothing to see here. So we did actually get to the last phase of this process. We are now going to use a method and it's called logarithmic differentiation. And it's going to be used to differentiate wild and weird exotic powers of x, amongst other things. That's one of its really, one of the things it's really good at doing. So let's show you. I would like to differentiate x to the power of sine x. Now that is a really weird function. Would you agree? I'm not even going to put it into Desmos, but I'm pretty sure it's a weird looking function, right? The power rule does not work. The power rule only works when that guy there is a number, right? 4 minus a half, right? power rule works when the power is a number. It does not work when the power is itself a function of x. So I do not know the history of this. Sometimes no one knows the history of this, but some mathematician was the first guy, and guy means girl as well, first guy to try and figure out how to solve this. And they created this technique. And it's a sneaky way of getting around a problem. Right now, there's no way in the world I have a formula that I know of that will tell me its derivative, right? Nobody's figured out what it is. If you don't know the answer to something in science or engineering or in mathematics, one way you can solve that problem is by changing it into a different problem that you do know how to solve. You then solve that different problem and you use the answer to that solution to figure out the solution to the original one, right? The one you didn't know the answer to. So this is how it works. Step one, every single time, take the natural log of both sides. So I'm going to take this function and I'm going to take the natural log of it and I'm going to do it to both sides. And you might think, and I would have thought, well, you've made the problem even uglier and I still don't know how to do it. But that's not true. We're going to see that this works out well. Step two is simplify. In particular, it's always going to be the right-hand side. Would you agree that x to the power of something is basically this row here? So I can rewrite this fella as the sine of x times the natural log of x. Are you comfortable that that is him? Right? The log of something to the power of something can be written as the power here times the log of the base. Power times the log of the base. And that's step three. Step two. And then step three, differentiate. And you might say, well, how am I going to do that? We are going to differentiate using implicit differentiation. Well, let's see how this works. If you differentiate the natural log of y, don't you get 1 over y times dy by dx? You agree? The derivative of the natural log of y is 1 over y times dy by dx. Isn't that what you do in implicit, right? If there's a y, the answer has a dy by dx after it. And in this case, I also differentiate that side. And that's a product rule, which is pretty much what you tend to get in many of these questions. And so I have 1 over y dy by dx is differentiate this guy, you get cosine x, leave this guy alone, you get the natural log of x, plus leave this guy alone, you get sine x, differentiate by that, you get 1 over x, so you get that guy. So right now, all I know is that 1 over y times the derivative is this. Step 4. Multiply both sides by y. Now, if you multiply both sides by y, you get dy by dx, what you're after. Cosine of x times the natural log of x plus the sine of x over x times y. We're one line off the answer. Step 5. Replace the y. What do I mean by that? Well, isn't y also x to the power of sine x? So shouldn't that y be x to the power of sine x? So the answer we have is cosine x times log x plus sine x over x times x to the power of sine x. Now, that is amazing. That the derivative of this is in fact this guy. If you were trying to guess the answer, you'd guess an awful long time before you, by fluke, guess that. Would you agree? That does not look that close to that. I think the only part I might have got was the answer's probably going to have an x, sine to the x in it, right? I might have made that assumption. But would you agree that it's not that obvious at all where this bit comes from? But nonetheless, we now have the derivative of that guy. Pretty cool. So remember the steps. Take the log of both sides. Simplify. Differentiate. Multiply both sides by y, and right at the end, replace the y back with its original. So let's try another one. If you see one of these side by side with another one, you'll start noticing that they don't differ that much. So let's do an x to the power of x. Now, if I do my first step, I take the log of both sides. Done, right? So that's step one, check. Now, my next step would be, a little bit out of sync here, would be to simplify. And by that, we always mean this side. Would you agree this is going to become x log x? So step two says simplify, check. Step three is differentiate. Well, implicit differentiation. Differentiate log y, you get 1 over y dy by dx. In fact, aren't you always going to get 1 over y dy by dx in this type of process? And would you agree that this is a product rule? And so we have 1 over y dy by dx is equal to 1 times the natural log of x plus x times the derivative of that guy, which is 1 over x. So after a little bit of tidying up, when we finish differentiation, we're left with that. So there's step three, check, differentiated. The step four says multiply both sides by y. Do you see that's going to happen every time? So I'm now going to have the natural log of x plus 1 times y. And then that's step four. And the last step is replace the y. So it's going to be the natural log of x plus 1 times that guy. Finished. Although this is a really unusual process, doesn't it have at least a flow to it? Right? There's a 1, 2, 3, 4, 5, right? A 1, 2, 3, 4, 5. And it will allow us to find derivatives of quite exotic looking powers. Try to find one that's a little bit uglier. How about this one? Ooh, that's not pretty, right? X to the power of 4 over x. Take the natural log of both sides. Check. Simplify. Check. Differentiate. Would you agree in this question? No, I didn't write the x very nice, but would you agree it's a quotient rule? Right. So it's going to be an f dash g, take away an f g dashed over g squared. Right. If you differentiate 4 log x, you get 4 over x times, leave that guy alone, take away this guy times 1 all over x squared. That guy gets me 4, that guy gets me 4 natural log of x all over x squared. So I've differentiated. Check. Multiply both sides by y. Check. And then turn the y into x's. I probably, now that I've looked at this one, wouldn't I probably pull out a 4 just to make it look slightly prettier, but essentially the method's finished. Now, it's a very, very niche market, right? Implicit differentiation, there's a fair number of situations you may want to do that. Can you imagine that it's not that many situations where you're going to have a function with really weird powers going on, right? Really exotic combinations. But for those situations, like, you know, the ones where it arms, isn't this going to be your go-to guy? It's the only way you're going to get the answer. So here is an example. One more example. It's question 20. And the reason I'm picking this one is because most of the time you don't need to do anything. The guy you've got at the start is the guy you're going to use. But sometimes you can do a little bit better just to make your life easier. Now this guy is the square root of x to a really weird power. And I could certainly go through this process and it would work, right? Nothing wrong with it. And it wouldn't actually be that difficult to do. But I'm going to do one change. How on earth did I get that guy?
You change x to the power of a half, and then multiply that by 9x, so it's 9 over 2.
Right. Would you agree that this guy is a little bit nicer to deal with than that guy? A lot? Nah. You could probably do it without this. But at this point onwards, I'm not going to do this question because wouldn't this question really just be very similar, right? 1, 2, 3, 4, 5, off you go. You've got your answers. I want to focus on what little time we've got left with a special case. There's always special cases, right? And so here is the special cases. You can also use logarithmic differentiation, not when it's weird exotic powers like x to the sine x, right? The guys we've been doing. You can also use it for really ugly square roots and really ugly powers. So my next one's going to be a really ugly power. Now, could I differentiate that without logarithmic? Sure. Would you agree that would be a chain rule with a quotient rule and some really horrible things happening? Right? I would not want to do that as a quotient rule or as a chain rule. I don't think it would end well. So I'm going to do this guy using the same technique called logarithmic differentiation. And I'm not going to change any of the steps. I'm just going to do it with a really ugly square root. So step 1 isn't step 1. Take the log of both sides. Check. Now we get to simplify. Right, now do you see that's a big ugly square root? Can I split it? It's 2 square roots. Agreed? Okay. Try to find my lot. There we are. I'm going to use these laws to slowly but surely turn this into something much nicer to differentiate. Would you agree it's a top guy divided by a bottom? So it could be the square root of x minus 2 cubed, take away the log of the square root of x to the 4 plus 1. Are you comfortable with that? And aren't square roots half powers? So won't this be, and I'm putting in every line I can think of, the same thing as that guy? Take away that guy. Are you comfortable? Half powers. And now we can use the third law of logs, which says it's that guy. Take away that guy. I think that's as good as that's going to get. Agreed. I can't really simplify it anymore. So let's move on. That's step 2 done. And differentiate. You're going to get 1 over y log y. This fella here, and well, you get 1 over the thing times 1, so I won't do anything with that. Take away, there's a half. This guy gets you 1 over x squared plus 4, but it is a chain rule, so you do finish with the 2x. So this fella ends up being him. That actually cancels with that, so I end up with that guy. And we have finished differentiation. Multiply both sides by y. And then wouldn't you replace the y by the original? Since I'm lazy and I don't have enough room, can I kind of combine the last 2 steps into one process? The derivative of this guy ends up being that guy. Now, if I try to do, there are other ways to do that, right? But this one is quite elegant, isn't it? Gets you kind of where you need to be. And for situations where you have some really ugly combinations, like that one, I could differentiate this function, couldn't I? And wouldn't it be a quotient rule involving a product rule involving some chain rules, right? Pretty much got everything going on. And it would be horrendously long and messy. So I am going to use logarithmic differentiation on it. So you take the natural log of each piece, which gets me that. Since I'm running short of time here, I'm now going to turn that into its simplified version, and I'm also going to do it all in one go. Are you okay with that line? There to there. Right, once you do enough of them, you just start getting quicker. Right, time to differentiate. This guy will just get you 10 over x minus 1, technically times 1, so it doesn't matter, plus 11 over x plus 1 times 1, so it doesn't matter. Take away 12 over 2x plus 3 times 2, right, because this time the inside function does have a derivative that's not 1, right, it's equal to 2. And what we got here is 10 of those guys, 11 of those guys, take away 24 of those guys. And I'm going to multiply both sides by y. And wouldn't the last step be replace y by all this stuff? Okay, I cut a couple of corners here, but 1, 2, 3, 4 lines. Right, 4 lines to get the derivative. If you had tried that as a chain rule, product rule, quotient rule combination, do you think you're going to do it in 4 lines? Nah. In fact, if it was me, I'm not even sure I'd get it right. I'd probably screw up somewhere, right? I'd forget one of the chain rules inside a chain rule, or whatever. I'd forget something. There're just too many balls in the air. Logarithmic is a niche market, right? It's not going to be something you're going to use an awful lot, right? But for the places that it does get used, it's really cool, right? It does get you the answer to quite pretty things, right? Last name.